There, now we're back in. So let's start with the share. Okay. All right, back here. I normally like to record these and I forgot to start the recording for this one. So dimensional faults from welding, like I said, distortion or warpage. Avoid this should ensure accuracy of preparation, adhere to weld specs and procedures, and use jigs and braces if needed. So if you have to clamp this piece down to a table to keep it flat, clamp a bar across it here, clamp a bar across the other side, then do your welding, and then slowly cool it down after your welding, then sometimes that's what we have to do. On a piece like this, sometimes it's hard to avoid distortion, so we have to sometimes re-distort it, which what I would do in this case would be to clamp it down to a table, make sure everything is flat how I want it, take a torch or something and warm the whole thing up, cover it in a welding blanket and let it slowly cool down, and that should help control the stress inside of it and should result in a better product once we're done cooling it. So that's how we can keep things a little more straight. So dimensional defects after welding. Sometimes we have welds that are too concave. So they are below the plate surface or it's just not what we want. Sometimes we got welds that are too convex, that great big belly on them. Overlap, cold lap. So there's some weld material that's kind of fallen over the edge, is laying on the steel, but was not hot enough to bond to the steel. So it just kind of lays on top of the steel, forms a bit of a connection. It kind of bonds to the mill scale a bit, but it doesn't form any actual real bond or weld. An undercut. Undercut is a big one. So undercut happens when we have too fast of a travel speed. An undercut is going to be kind of seen right, well, it's not undercut. Undercut can be basically if we want to have all this material nice and straight, but when we look at our top wall or our edge there, there's a line where we've burnt that material away and not filled it back in. And that is usually travel speed. You're not allowing that weld to fill in as you move over it. You're moving fast enough to cut it away, but not fill it back in. That's what's happening there. So convex welds. So they are too big and curvy. Excessive convexity will create a hard spot and causes a notching effect. So that notching effect is going to happen right here. And it's also going to happen right here. You can also see a little bit of it right at this spot. What's happening is we have too hard of a transition from the steel to our weld. It's not a nice smooth ramp. What it is, it's quite the abrupt change in direction, and that's not good for stress lines, for basically continuity in the weld. If there's going to be stress in the weld, we want to be able to flow nice and easy. When we have cuts like this, cracks, notch effect here, it's going to be a hard spot where the stress is going to basically change direction really quick, and that'll eventually be a failure point. This notch will open up, crack all the way through. Same with here. When we put a lot of weld on too, the stuff, it shrinks and it causes stress in the weld zone. We can see that. We see lots of different layers here, right? I see at least 5 different welds there. And if that's 3/8 plate, that's the maximum you want to have, but you don't want to have this much convexity. You want to keep it just over flush. So concavity and insufficient throat. So your weld being concave, it just means the face of your weld is below the surface of the steel that you welded. So that's a discontinuity. That's not considered a complete weld. So to consider this a complete weld, we have to be at least to the surface all the way across here. If this ends up happening to us, if we're pulling some flat welds, some weaves in the flat position, and it ends up being too low like that, we can fix it. We can run some passes over top of it, stringers, or even a small weave if we need to. So there is corrective measures we can do for that. So a concave fillet weld, that is right here. You can see it's got that kind of bowed-in shape. Well, some situations may call for a concave fillet weld. And having a concave style fillet weld is not a bad thing when we are dealing with something with stress. Because if we had this being convex with a little belly on it, what happened is, especially come through here, hit this notch effect, travel through the weld. It would basically hit another notch effect right here, then travel through, and those would crack and fail eventually. So when it comes to some stresses, welds like this that are convex allow a more smooth flow line. So it's not necessarily a bad thing. It's a bad thing when it's not where we want it, but you know, if the situation calls for it, then that's what you give the person. Overlap or cold lap. When weld exists outside of the fused area. This shouldn't be showing up like this. Is converted and is not great. But basically, it's just using this baby and this little Shar-Pei puppy as an example. So if you're welding away and you get some weld that overlaps and touches, say, the base metal, but there's not enough heat to bond it to there, that's a bad thing. That's called cold lap. And it's, yeah, definitely a weld defect that we don't want. And it's just a cute picture, and everyone likes puppies. So, yeah. So on this picture here, it asks, can you see where the crack will start? And we've got a couple spaces that, you know, well, one space in particular, the crack's going to start, and another really bad deformation on this weld too. So right here by my cursor, if you can see my cursor, that is where the crack's going to start. It's going to crack right through. Depending on how the stress is applied, there could definitely be a crack forming across there as well. This could even, you know, just connect to that one, shear right off, and then that's all sorts of bad news. What this shows here is cold lap on the bottom. This is a defect. What happens is they welded through. Oh, no, it's not cold lap, it's slag entrapment. So they welded through, and there's a couple dark lines that run either side of this. They're fairly easy to see. That is going to be a discontinuity. And unfortunately, that's the first pass you put in. And you created that by putting the second pass in improperly. So we got to get rid of that. So what you got to do is you got to grind all this right out and then redo this and make sure we don't have any issues in that first pass area right there. So that's a pain in the butt. Here, excessive buildup. So we're not supposed to have any more than 1/8 reinforcement above our plate. And this is showing here that this is a lot thicker. This is done with an X-ray, and different densities show up as different shades of this kind of gray color here up on the grayscale, and real thick parts are going to show up like this. External undercut. What you're going to see is this is not able to transfer image back to the film that's being developed because of this discontinuity here. So that's how we identify things like undercut on an X-ray. It's pretty interesting how it's done, but you definitely don't want to see something like that on any weld you're ever having X-rayed, because that's going to be an automatic failure. So surface defects. We got surface porosity. We got badly shaped welds. We got ripples in the welds. We got excessive spatter. We got craters, stray arc. And the weld just generally looks kind of ugly on the outside. This animal here is a fine example of that. It's got, you know, beauty is in the eye of the beholder, but yeah, that's something. That's something. I wouldn't want my welds to look anything like this animal. I think it's a cat, maybe a dog. I really don't know. I wouldn't want it to look anything like that, anyways. Basically, if your weld looks bad on the outside, there's a good chance there's something wrong with it on the inside. If it looks good on the outside, there's a good chance it's okay on the inside. So porosity, kind of talked about that yesterday. We purposely made some, turned the gas off, and this kind of aligns with the picture that I showed you. There's a bunch of holes in it, a bunch of garbage. In an X-ray, it's going to show up as a bunch of dots, kind of looking like freckles, dark spots. And that's not what you want to see on an X-ray. Definitely not what you want to see on an X-ray. This is done in a cluster. Sometimes we get it as a line, depending on if there is an ongoing issue. Say if you had no gas the whole way, this whole X-ray side to side would have these dots in it. This here, that could have been wind blew the gas away for a brief second, or wasn't quite clean, and there was some stuff that burned inside the weld, say a bit of oil, and it reacted with the welder, created some gases. Gases got trapped inside that weld when the weld metal cooled, and that created cluster porosity. So that's how that would happen. We have longitudinal cracks. So what that means is this running along the length of the weld, and the longitudinal crack is here, and that's going to be right down in the base metal. If we don't have a good bond here, with all this weld up here, as it cools, it shrinks, and it's going to pull and create stress, and this is going to crack open here, and these edges of this plate are going to lift on either side slightly, and it will no longer be flat. If you have a good bond here, it shouldn't break, it should stretch, but if you don't have a good bond here, it'll create a crack line. You'll see it, it'll show up just like that one. Transverse cracks. I've never had a transverse crack in any of my welds. I don't understand how it happens, but it's just a crack that moves from side to side across your weld. I have seen transverse cracks in certain types of welding. Now, if we're putting hard facing on a loader bucket, let's say, some of this material that we're putting on is so hard, it's prone to cracking. And it will crack transversely like this. But it's not necessarily a bad thing. As long as it's got good connection with the base metal and it's not spalling off or chunks of it aren't breaking off, then that's fine. This stuff is just so hard and brittle sometimes when we're putting that hard facing on, that if you don't cool it absolutely perfectly, it's just going to crack a little bit. It doesn't mean the weld has to be ground out and redone if you're doing hard facing. But yeah, it's not something we want to have in something like a 7018 weld. I've never seen that happen in a 7018 weld. All right, so we're going to go to burn through. Burn through just means, you know, we have our burnt through the plate, we got a small hole in there, and we weren't able to fill it in entirely. When I did a weld the other day for my 20 levels, I had some burn through in the root, and it wasn't great. Internal root or root bead undercut. So we're trying to push that weld out the bottom of the plate, and when we're doing a groove weld, the whole goal is to get a nice little weld on the underside of the plate, and we weld that from the top side. It's crazy. So we point our MIG gun straight down into here, we weld this bottom section, and we should have a nice weld shape on the bottom side. But if we don't get that in there, or say we're leaning to one side more than the other, we'll get some undercut there, where we'll have a line of complete or incomplete fusion. And then if we x-ray it, it's going to look like that. It'll show up as that line. So that could look a lot like the longitudinal cracking. So it really depends. Sometimes we'll put a mechanical instrument inside of these pipes. If this is a pipe, sometimes they'll use what's called a pig, and they'll jump it and they'll put it in there, and it's a little robot. It'll travel down and inspect the welds as they go down. So it'll take video of the inside or pictures, and that helps to inspect the inside of a pipe. Internal defects. So internal defects can be laminar or spherical. So laminar is with the steel, spherical, obviously this little pinhole, gas pockets, wormholes. There's the arrow bar I was talking about. So laminar defects are cracks, insufficient penetration, things like that. Yeah, so this here says she ain't pretty, she just looks that way. When earlier I mentioned that, I said if your weld looks good on the outside, it's most of the time is good on the inside. There are times where it may not be good on the inside, and we could have this situation. You got the nice surface, you can't tell there's anything wrong on the inside, you crack her open, and it's not a solid chocolate bar like you wanted, it's an arrow. You know, in the welding case, it'd be all full of porosity, and that wouldn't be a good thing. So we're gonna move on past that. Oxides, scale, porosity, stuff like that. We get these forming and stuff. The big thing, prepare and clean your steel. That is going to help you out. Things like these bits of porosity. We need to always also inspect the end of our gun. In that video I did the other day, I was talking all about the gun, and I showed the bits of slag at the end of it. We need to clean that out. We don't have to clean it every single time, but starting to build up in there, we need to take care of it before it becomes an issue. Slag inclusions here. What this is this person did not clean out their weld entirely and properly the first time. If you can't get it with the chipping hammer and the wire brush, we may have to move to a grinder and grind some of the stuff out. But if it's, you know, an important weld, a make or break weld, then we need to take all the steps we can to make sure that there is no slag inclusions. What this is, looking here, so we got this bit of slag, this bit of slag, and this bit of slag, and it's all kind of transverse, which means it runs across the weld, not with the length of the weld. What this looks like is a person was using stick welding, finished up with the stick rod, put a new one in, started welding without chipping the slag cap, finished up the rod, put a new one in, started welding, put a new one in, started welding, and they just got a little bit of slag inclusion on every time they restarted the rod because they did not chip and clean that area where they restarted. And when they sent new weld metal down, it laid over top of the existing slag and trapped some of it, wasn't able to all come out. Tungsten inclusions. This is what I get in my welds all the time when I try and TIG weld. I am new to the world of TIG, fairly new anyways. And what happens here, tungsten inclusions are when you get too close to your tungsten and you touch it to the steel, and what happens, a little tiny bit of it just burns off or breaks off the end of your tungsten and gets stuck in your weld. It's super hard, way harder than the steel you're welding, and it shows up like a star in the night in a, what do you call it? An X-ray. Yeah, you don't want those. That's why I don't do anything TIG that's ever X-rayed. I will never do that. Maybe when I'm better, but not right now. Laminar defects. So it's a defect that runs along the length of the weld. Here we have a crack. So what's happened is we have a base metal here that's nicely bonded. We had a base metal here that was nicely bonded, but for some reason it shrunk, pulled away, and cracked. So that's not a good thing. Here we got the weld pulling away from this side. We got the weld separating here. That's going to run down, maybe not the entire length of the weld, but it's going to be something bad. In this case here, yeah, we got some great bonding here. This is all cold lap on the bottom. It's just kind of laying there. The person never pointed the welder at that. All they did is pointed it at this back wall and laid it in there, and wasn't able to get a good bite here. And then obviously we would have liked to have fusion into this as well. And then if we would have worked on the other side, we would have had more fusion into here, being a nice, you know, solid 100% full penetration weld. Not the case in the picture we just saw. Here, inadequate or lack of penetration. So this is where these X-ray guys really shine, is they're able to identify all these different ones quite easily, depending on how they set the parameters on their machines. But inadequate or lack of penetration is easy to see and tell because these lines are going to be very square edge, like very hard and straight, and they're going to be almost perfectly parallel because that joint fit up before we welded it would have been a parallel fit up. This person did not get down through here far enough on the bottom to get that weld. It can be difficult. It's not that difficult, but if you don't have good preparation, you're going to fight it the whole time. And so taking the extra few minutes to prepare your welds properly is definitely the way to go. I am not a great welder by any means. I can weld okay. But the other day I did a flux core weld for my 20 level class, and I haven't done one of these in a long time. It was a flux core 1G. So it's an open groove, very similar to this situation here. I take the S6 wire, because we put a hard wire root in there, point it straight down in this gap and weld this gap shut along the whole 6-inch plate. And it's got to look good, can't be too drippy. And then we put cap and fill on with flux core. I did that, and that actually turned out really well the first time. I got lucky, I would think, but the preparation is really what saved me. There is no inconsistencies in the preparation. Everything was the same. It was predictable. And once you figured out how to get that weld not to fall through all the way, like out the bottom, you get to fall through the amount you want. All you had to do is repeat that process the whole way and just not change anything. So setup and preparation, definitely key factors. This here, it calls it offset or mismatch. When I hear offset, all I think is, you know, dude from the Migos looking like he's dressing from a tickle trunk every day. Yeah, not a super big fan of that guy either. I've been hating on some of these rappers lately. KSI, well, he isn't even a rapper to start with, but yeah, it's a nice story. What I call this is high or high-low. And what happens is this plate is slightly above this plate, and it's not cool. So we don't get a very nice joint here. So what I do is when I tack this up, I take over the anvil, I give it a smack with the hammer, and I make sure that this plate here is the exact same level as this one. And you just run your fingers over it, you can feel it. Adjust it a few times if you need to. If it's really bad, bust it apart and start over. You're never gonna get it absolutely perfect, but it doesn't mean we can't try and do our best to get it as good as we can. Working with this just kind of shows me that you don't really care much. You just tack it together and slam the weld in there and call it good. Spherical defects, the round ones. So that's porosity. That is inclusions, slag, spheres, stuff like that in our weld. So it's going to be small little holes. We're going to cut it sideways. You can see this one here. There's some big holes in there. That could be slag inclusion. This one, we got little spheroids of gas in here. We also have a big crack. We don't want that in there. Porosity. Causes of porosity. Surface contaminants, oil, paint, galvanizing scale, etc. Bad rod. Now, compromised rod is what it says here. Bad is just a term that we use, but basically with 7018, it has to have a very, very low moisture content. So it comes in a hermetically sealed package, which means they vacuumed the air out of it and vacuum sealed that pack. So when it gets to me, it's fresh, there's no moisture in it. I open it up, expose it to the air, and then I put it in my rod oven. So I have a rod oven in the classroom here that keeps rods at about, I don't know, 40 degrees, 35, 40 degrees Celsius. But what that does is keeps the moisture out of them. It just slowly cooks off any moisture that might even try and enter the rods. It just slowly gets baked out. So when we take them out of the rod oven, they're great to use. What we can do is we can leave some out in the middle of the class for a week and then compare them directly with ones from the rod oven, and we can see the difference in the welds. It's not a huge difference, but if you're doing something like a very important structural weld that needs to be completely sound, then it is something you want to do. On big job sites, like when I was in Fort McMurray, I had to have a rod oven with me at all times. My rods cannot be exposed to the air for more than 1 hour. If they were, I had to discard that whole box and then get a new box. So I was always continuously lugging around my rod oven, plugging it in, keep my rods warm, but that's what the job required. So if we have a clown in here who's sending out that link again, I suggest you stop it. If Vaughn is one of my students, then they need to enter their actual name to come into the waiting room, because I will not let anybody in who doesn't have a proper name. So what we're gonna do is we're gonna view the waiting room. We're gonna see Vaughn, and since Vaughn is not one of my students, we're gonna remove him. Remove, and done. iPod is in the waiting room also. I don't know who iPod is, and that person's not using their proper name, so we're gonna take them out. I don't want to go through this again with you guys. That was not fun the first time. It was a real pain in my ass, and that's why I put the waiting room on in the first place. So if we're gonna be doing this again, yeah, there's definitely gonna be some issues going forward. So let's get back to it. On a happier note, causes of porosity, like I said, surface contaminants, oil, paint, galvanizing scale, bad rod, lack of shielding gas, slag entrapment, tungsten inclusions, which I do all the time when I TIG weld, copper carbon inclusions from carbon arc cutting, and improper manipulation of the rod. You let that puddle, or you let the slag get ahead of your rod, you trap some slag in your weld. So, oxidization caused by lack of or improper shielding gas, typically TIG. Lack of fusion, mostly an issue with short circuit transfer. So yeah, it's not the best here, but yeah, this is all defects. So what we can have here is incomplete fusion. So what this slide is showing here is that we are not getting down to the complete bottom of this weld, and there's a hole in the bottom. That's not what we want. Here, we got a couple gaps on the side where we didn't get in all the way. Right here, tucked right in that corner, there's not any fusion there. And right down here, we never got the bottom of this. A couple ways of fixing this. You open up the angle a little better so you can reach down to the bottom, or you come back from the bottom, grind a bunch of this out, and weld it from the bottom, welding it from both sides, if you have the ability to do so. Crater cracking. These refer to star cracking that occurs at the finish of a weld. Crater in welding terms is basically you finish your weld, you don't let that kind of crater backfill, and you pull out of it real quick, and it just leaves a depression in your weld. That's a crater in kind of welding terms. But make sure you fill the crater before terminating the weld. So at the end of your weld, when you're welding, pause for just, half second. It fills up that crater, then you stop your weld, and you don't have that big crater crack at the end. So that is that for that. So what we're going to do here, we're going to pop out of this. We're going to stop sharing. We are going to put this on pin. Actually, no, I'm not going to stop sharing. I am going to share my screen, and we are going to open up a different screen here. Let's go here. Let's go to share. Let's go to escape that one. I'm going to go here. Weld Defects video, that is now available for you guys. Defects quiz will be available for you guys. So the video, this one I like. Top 5 reasons why your MIG welds suck. It's a good one. It's a short one too.
Hey guys, it's Matt from East over here in my home garage. We're going to do another quick little fun welding video. It's the top 5 reasons that your MIG welds might suck. So let's get started. Number 1 reason that your MIG welds might suck. So if you're getting a black sooty ring around your weld, maybe it's spitting and popping back at you more than usual, or you're getting some kind of pitting or pinholes in the actual weld itself.
Yeah, I think it's the same one. Letting other people in. It's that waiting room. Perfect for that shit.
If you're seeing a sooty ring around your weld and everything on your welder settings,
No, they're just sitting there like, why can't I get in?
good chance that you have
I don't think so. Because I've approved them to come in to do anything. So they're just sitting there, like they click the enter link and they basically just wait. And it'll say like, you have to wait to be admitted or something like that. And then, like I told these guys, if you're not using your real name, I'm not letting you in. Yeah, so iPhone, I don't know who you are. I had one kid do that earlier. His name is Sebastian. He goes, oh, hey, this is Sebastian. Cool, awesome. I've been trying to get you in here for a week. Come on in. I'll make exceptions in that case. But Vaughn? I don't have a Vaughn. And I don't, yeah. So.
This is a clean piece of metal that I hit with the grinder, cleaned it all. Should be good, but it has some grease or residue on it that we maybe didn't notice or got on while we were working on it. And while we were welding, you will notice that it created that black soot right around it, actually made the grease kind of bubble up and get more liquid-like. And now you can really see the grease on there, whereas before it was just a real fine film. So that is a good instance where if you have a part that maybe was in use, but it seems like it's clean, but it has some oil on it, or maybe you sprayed some oil on it to keep it from rusting in the shop, that could happen. So the solution for these two is basically just to clean the metal really well. Make sure that you're using low VOC pre or acetone to wipe the panel down after you clean it with an abrasive method, whether it's a media blaster, an angle grinder, a DA sander, something to take all of that off, because you don't want to weld on something that has rust present. Even though the welder will be able to burn through the rust, you will get a weld that is porous and also is going to have a bunch of soot on it, and it's not going to be a strong weld. Now, the last thing that could cause that is lack of gas flow. It may give you a false reading. So if you have too little gas, or you're out of gas, or you have a restriction in your gas, a common one that happens to me, aside from just not watching my bottle and running out of gas, is sometimes my nozzle will actually get a bunch of buildup of spatter on the nozzle from welding. And you may be doing a ton of welding, you don't notice it. Next thing you know, you're getting porous welds or getting soot around the weld that gets dirty, check your nozzle or your consumables. Sometimes they get blocked up and it actually will block the shielding gas that's coming out of your MIG gun, and that could be causing your problem. So it could be as simple as just threading the nozzle off, cleaning it out on the inside, putting it back on, and you're up and running. So check one of those things, and usually one of those three or a combination will be what causes your problem. The number one reason MIG welds might suck. All right, second reason that your MIG welds might suck. If you're having problems with your welds sitting high atop the metal that you're welding where they may just knock off easily with a hammer, we have little piles of welds with a gap in between them. There's a few things that can cause that problem, and usually one of these are what causes me issues when I see that. So the first thing is simply the settings on your MIG welder. Getting a good MIG weld consists of mostly technique with the actual welding process, and more importantly, the settings on your machine where you're blending the voltage or heat with wire speed or the wire at the rate that the wire is coming out of the tip of your MIG gun. So when you blend the two of them together, you should get a really good, even weld that's going to sound like frying bacon sounding. You're hearing spinning or it's pushing back at you. You may either have your heat or voltage set too low, or you may have your wire speed set too high for the heat range that you're currently in. You want to take a look at your machine. For instance, these machines, inside the flap of all machines or on the side of the machine, there is a chart that's like a suggested settings that will get you started, and you can always dial in from there for your technique and your skill. The other thing that can cause that is a technique issue. If you have your wire stick out too far, or you lift your hand while you're welding, or you start too high from the panel, you may have too much stick out and it's actually dropping the power. Even though you may have the machine cranking all the way up, you may be dropping the power of the weld because it's causing more resistance to jump across that long piece of wire that's sticking out there. What I like to do is use my MIG pliers and actually take them and run them against the back and cut them, and that will cut your wire to a good length, which is about 1/8 of an inch stick out from the end of the nozzle of the MIG gun. The other thing I like to do is try and keep a nice, steady, consistent height off of the panel with the tip of your MIG gun. So I usually like to be 3/4 of an inch to an inch total distance off of the panel, and you can adjust from there. That's a good starting point. And for you, you don't want to be too much more than like an inch or a little over, because you might start having that problem where it's going to start spinning or piling up for you. So if you go through those different things and see which one is causing your issue, a lot of times you will find it's one of those super easy to correct, and you can be back welding and getting a nice strong weld. Number 3 reason that your MIG welds might suck is travel speed. Traveling too fast or too slow can create weak weld and also something that doesn't look good. So I did a weld here where I moved far too quick across the panel. I had the correct settings as per the recommended settings on the welder, but I traveled across the panel far too quick. What you see with the weld is that it's kind of drugged out and it gets very thin, and there's even almost some gaps in the weld along the way. And then finally, as I started moving extremely quick at the very end, I was actually moving quicker than the shielding gas was able to cover the area, and we started seeing some porosity in the weld at the very end, which obviously is going to be a problem. Now, if you're moving too slow, it's the opposite effect. You're going to start to blow through the panel. If it's something that's thinner, you may get a lot of warping in the panel, it may heat up, and your weld will get extremely large. You need to find a happy medium where you're moving across the panel, pushing the weld as you go, making sure that you're kind of circling back into the weld to get nice overlap so there's no pinholes or gaps in the weld, but you're also not burning through. That takes a little bit of practice as you go, but if you get the welder set up as per the settings and tweak it from there, you can usually get really close by just doing a little bit of practice along the way. So if you make sure that you practice this one, there's not a lot that you can do as far as changing the welder, but it's more just sitting down and doing a lot of practice. All right, number 4 reason that your MIG welds might suck. If you're having problems with welding sheet metal in a butt weld situation where you're blowing through, as soon as you hit the trigger, it just blows through, you have a problem. There could be a couple of things that could be causing that problem. The first and foremost thing that I see a lot of times, even with people that have been doing it for a while, is the fit up of your panel. You need to make sure that when you're doing a butt weld of a panel that you have very little gaps between the panel and that if there is a small gap in a panel, it is no larger than the size of your MIG wire, and it is a consistent gap across the panel. If you have a gap where you have a jagged edge that's cut and it goes from being too tight to open to tight again, you may have issues where you may set the welder up for a good fit up of your panel, and when you go to an area that has a big gap, it may just blow through. The other reason is that there's nothing holding the panel from the back side, and you may blow through the panel because as soon as it touches it, the two edges that are cut, the gap, they are going to burn away very quickly, and they'll just blow a hole in the panel. So if you have a situation like that where you have too big of a gap, you've already tacked the panel in place, and you're kind of stuck, you can either use a copper backer to stick behind the panel to basically back the weld up, and it will help fill the weld up, and the weld will not stick to the copper backer. Or in some situations, if the gap is pretty small and you have a piece of filler wire that matches the gap, like I have here, I have a piece of 3/32 TIG wire that I laid down into this gap, and it filled up the gap, and then I used that as my filler. Instead of trying to cut a sliver of metal and fit it in there, you can use a piece of TIG filler wire as your filler material, MIG right on top of it. It will burn the filler wire into the weld as well as your MIG wire. It will fill it up and save you from having to cut the panel apart and redo it. But usually between those things, that's what your problem is, aside from just having your settings incorrect. The fifth and final reason on why your MIG welds might suck, or you're having a problem with your MIG welder, could be something that you wouldn't have guessed. That is the input going into your welder. The power supply or power source that is coming into your welder could cause a problem and make your MIG welds suck. So you need to make sure that you have a proper breaker for your welder. Whatever welder you have, it will be in the settings or in the instructions that you can see what it requires for that welder. Now keep in mind, if you're like me and you use multiple types of welders, you want to make sure that you have a breaker that can handle all of those types of welders. So I use a MIG 175 for my MIG welder. That can actually handle a 30 amp breaker, but I actually have the TIG 200 for my TIG welder, which I think needs a 50 amp breaker because I tend to do long runs at close to the max of that welder. So in that instance, I want to put a 50 amp breaker in my shop, and that's what I have. If you have too small of a breaker, like you're trying to piggyback off of a 220 line that's maybe running some home appliances like your washer, dryer, something like that, then you may have an issue where that breaker is too small and you may be popping the breaker. Another issue at the source within your building or shop where you're welding is if you have poor or old wiring. If you have an electrical system where maybe it's piggybacked from your house or from another source, or it's just really old wiring, there may be a drop in voltage every time it goes through those connections, and by the time it gets to your welder, you may not be getting the power to weld correctly, or maybe your welder won't even turn on. The final thing that I see is probably the most common thing when we have calls or I've seen issues with welders as far as the power supply goes is the extension cord that you're choosing. Not everyone has a shop where you can have a 220 outlet right by where you're welding, and if you're like me, you probably have a bunch of projects you need to move the welder all over your shop. In that case, you need to have an extension cord. Make sure that you're using a heavy-duty welding-rated extension cord. For my MIG 175, I have one of our 220 welding extension cords that has big, beefy wire in it that can handle running all the way across my shop without having any issues with dropping in power. The most common thing also is 110 welders because it is so simple to get an extension cord. If you're running a long extension cord, like 100 foot or 200 foot to your welder, do realize that you're going to be dropping in power by the time it gets all the way to your welder, and you can't use an extension cord like you would use to run your Christmas lights on your house. By the time that the power actually gets to your welder and draw that the welder has, you're going to have issues with your welder where you're going to get poor welds, maybe your welder won't even turn on. So make sure you're checking the electricity in your shop. You can use a multimeter to check that if you want to check out and make sure that everything's adequate, or just take a look at all of your wiring as far as extension cords go and be sure that they are up to par. That's all I have for the top 5 reasons that your MIG welds might suck. If you want to check out all of our welding supplies and welders, you can click the link down below. You can visit eastwood.com to get all the tools you need to do the job right. Thanks, guys. Catch you later.
All right, folks. So that is that for today. Thank you everyone for joining. If you guys could drop your names in the chat, that would be awesome. I do appreciate it. And yeah, so as you guys may or may not be able to see earlier, I had a couple people ask to enter the waiting room. You may have heard something about it. People that were not, well, I don't believe to be part of this class. So when entering these classes, use your name, or at least have something like Sauger has, Snowman Sauger in his name. I know that's going to be Sauger. I got someone like Vaughn or an iPhone trying to log in here. Chances are, unless you messaged me saying, hey, it's me, Mr. Scott, like say via an email, I'm not going to let you in. We had issues the first time, and now I got more people trying to access it. And that's not something I want to detract from your guys' learning experience. So that's kind of why I've implemented that waiting room, and it seems effective. I've been able to keep, people who shouldn't be in here out of here. That was a bit about weld defects and things like that today. And that was kind of inspired by that no gas weld we did yesterday. If you haven't had a chance to look at the pictures of the welds from yesterday, they are in that folder with all of yesterday's stuff. Please get that quiz completed. Yes, Sauger is fine. I am okay with that because I know it's you. I know that you have your name in there, so that's fine. Yeah, so I'm okay with that because I know you've been here for a while. Yeah, but people like Vaughn, I don't know who that is, or iPhone, that could be anybody. So I don't need them in here. So that's why I do this for you guys. The waiting room does kind of suck because, people like, well, some people might show up near the end and not be able to get in immediately. Then they got to wait for me to let them in. And it happens. But once again, thank you guys for being here today. I really appreciate it. If we could take care of that quiz, I open that one up for you guys. That'll be ready. And yeah, have yourselves a good day. We need to make sure we're taking care of all of our quizzes though, because there are a few people in here that have not been completing the quizzes. They have been showing up to classes, which is awesome, and I really appreciate it. Thank you. But I can't give you marks just for showing up. I can give you a few, but not enough to justify a credit. So I have to have some actual work completed on your guys' behalf for me to be able to mark you as successful, and so you guys can complete the course. And fabrication is pretty cool, I think, especially when we get to like 20 level, because it's full semester. We get to do a lot of neat stuff there, and we get to expand on all the basics we've learned. So if you are interested in this, I know it's been a rough go with this COVID and online learning. And it sucks not having you guys here. But if you guys want to learn a little bit more about welding, I invite you all, if you are successful in this course, come take 20 level. It's a great space in the shop. We do a lot of fun stuff. And 20 level, we've got opportunity to do a lot of cool things. If we have our competitions back up and running, there's Skills Canada, there is a welding rodeo, there is just, a bunch of fun we can have. And 30 level, we do get to build our own projects, which is going to be pretty neat. That's a fun one. So whatever your mind can come up with, as long as it's feasible, we can work on one of those in class and get that done. And kind of a cool idea I thought would be neat for you guys is if you guys have taken construction 10 and you've taken fabrication 10, continue to take those all the way through 20 and 30 level. And in 30 level, if you can arrange for those in the same semester, your final project that you create, you design and create, can be a combination of wood and steel. And essentially you'd have double the time to work on it because you'd have a period of fabrication and you would have a period of construction. So I've already spoken to Mr. Lawrence and he thought that was a really great idea. So something to consider for the future. I know it's a couple years away, but it's always fun to start planning things like that. And I'm trying to grow the program as much as I can, make it as interesting, as engaging as I can, because not all of us learn from books. I'm a hands-on guy. I recognize that a lot of people in here are similar to myself when I was younger. I did not do well in the in-class settings, but you gave me something I could put my hands on, and I had all sorts of fun. So thank you again. I appreciate it. I'm going to stop the video and I'm going to mute. If you guys have questions, just yell at me, send something through the chat, whatever you guys have to do to get my attention. I will be here to help you. But I'm going to shut this down and I will talk to you guys tomorrow. Have a great day. I'll see you then.